Welcome everybody, Joseph here with you. So today I'm more excited to share with you the core behind what I can call the backbone of artificial intelligence. So as we see on our screen here, this constitutes what we shall discuss. It has been summarized into these different sections. But to guide our discussion furthermore, we shall look at how these different concepts relate to real world scenarios. In this particular context, we shall look at gate analysis as used to predict, to give the likelihood, whatever, for a musculoskeletal well-being disorder or disease. So we shall look at from the beginning artificial intelligence, how it has evolved over time. We shall also be able to define artificial intelligence. When we define it, we shall be able to see how we can test its presence using tests like the imitation game, arguments like the Chinese room argument, and see even the contrast between the two, how they understand intelligence. Beyond that, we should also be able to look at the four major dimensions within which artificial intelligence makes its backbone, where a system can either be thinking humanly, can be thinking humanly rationally, or acting humanly or acting rationally in any case. More deeply, we shall look at how acting humanly looks like, because this is evident in the current artificial intelligence systems we have at hand. With that said, we shall also be able to look at what an artificial intelligence technique is. Having understood what artificial intelligence technique is, we shall be able to look at it in a way of problem solving. In problem solving, once we define a problem, analyze it, and represent the knowledge within its domain, we choose the best technique that guides us in how problem solving will be handled in this artificial intelligence technique. Knowledge representation captures more of our attention, because we shall be able to see how we shall represent the knowledge in our gate analysis system, and be able to give different solutions. In those different solutions, we shall analyze the best. So to look at problem solving, we shall look at some such strategies and how they approach problem solving. We shall also look at the different artificial intelligence approaches, and look at the Gardner's multiple intelligences that are 8 in number, and we shall look at majorly the 4 that seem to span in this current status quo, that's gate analysis. In this particular context, we shall look at areas like linguistic, the mathematical aspect of it, vision majorly, computer vision, and then the kinesthetics. As bodies move, we shall also to study the movement. With that said, we also look at how reasoning and uncertainty can help us achieve better models, decision making and planning, and then machine learning integration. Then finally, synthesis in gate in gate analysis will definitely be our last point of discussion. With that said, let's dive and begin with our first aspect about this. Well, talking about the evolution of artificial intelligence over time, it has been an idea that was a dream in different occasions, spanning from the early 13th century up to now. We've evolved over and over again, starting from Aristotle's vision of having self-moving objects that could solve tasks at their wish and could do what we need from them, promoting them to a class of becoming semi-gods. It was an artificial intelligence dream within his mind. To Leonardo da Vinci, who invented the humanoid robot that simulated artificial intelligence and its different possibilities. You see, over time it has been advancing into the current era. We see the more developed versions of artificial intelligence. Having briefly discussed the origin and how it has been in the ancient times, Now, what is artificial intelligence itself? Well, to give it a simpler definition for now, let's take it as the ability of a machine to seemingly think for itself. Seemingly thinking for itself, we shall make it to mimic human abilities of reasoning, be able to learn, reason, and then solve a given problem. We shall not dive deep into defining each term within this, because when we talk about thinking, we shall again expand our discussion. For now, let's keep it as a behavior where a machine can act seeming, I think, for itself. Well, having defined it as brief as that, how can we assess a machine to be intelligent? In other words, how can we know, how can we prove the existence of intelligence in a machine? Well, looking at the Turing test, where we have an interrogator with a uh, stranger, what can I say, stranger interrogatees. Yeah, in these two rooms we have a system assumed to be artificial intelligent, and then a human being, and each is required to talk the reverse about itself in opposite a machine to say about it being a human, and the other way a human of course maintains. So all of them assumed to be humans. So once a machine can able to convince the interrogator that it is a human, we assume that to be a kind of intelligence. The Chinese room management comes in and says, what if it is just a matter of having rule books with definition of each symbol, simply manipulating symbols to get an appropriate solution? Does that signify intelligence? Well, this again guides our discussion to the versions of the artificial intelligence that at hand, at the time one will be dealing with. Does that show a strong version of artificial intelligence, or it's weak artificial intelligence, seemingly a way of simulating understanding, one can say? Well, with that said, let us so dive deep and look at the different dimensions that artificial intelligence tend to span. And more precisely, we shall look at more deeply about acting human. But the major four include thinking like a human, and that means modeling human cognition. That needs more knowledge from neuroscience, how humans think. Therefore, that you should be able to first understand how human brain works and all the kind. And then thinking rationally, you have just sought it the right way, using logical reasoning. We shall be able to look at that in a short while. And then the last part of it is acting rationally. All these dimensions can be represented, are constituted in the Gardner's 8 different types of intelligence, and each can be seen simply as you dive deep and deep. To act human, just like I say, we shall talk more about this because it's evident in the current versions of artificial intelligence. It means a machine is acting like a human. So what comes to our mind when we say it's acting like a human? It should be able to do different human abilities. It should be able to speak. It should be able to learn. It should be able to see. It should be able to move if possible. It should be able to give an insight given what it has learned. That gives us to the diverse eras. I mean, the different ways in which we can see acting humanly is. And this again attaches us to the Gardner's types of intelligence, and where we look at speaking as a way of how can a machine give us information that it has represented initially in binary form? Can it now convert it to a way we understand? Can it learn how to speak? You know? And then also, can it be able to see from its environment? That is computer vision now. And then also, if we need it to move, we now implement robotics. from a discipline of engineering. So all these capabilities make a foundation for the advanced agents or artificial intelligence systems we have in our current society. So as per the ongoing gate analysis project, computer vision and natural language processing have become very key, because we can be able to analyze, like we need to capture information as one moves, can be moving in a movie. So we analyze his walking pattern. The computer should be able to see somebody's moving patterns within a given video or a given real life scenario. Robotics will not be part of our current idea of discussion, but most importantly is also natural language processing. Once a model lands, it should be able to give us a general, a human understandable explanation of its prescriptions given in an instance. So, majorly, how we shall represent our knowledge. Well, representation is very key. How we shall represent the different parameters that constitute, that are relevant for giving a conclusion on whether one is okay with this musculoskeletal system based on given attributes. So with that, then that can bring us to an understanding of what an artificial intelligence technique is. You know, when one talks about an artificial intelligence technique, it means it's basically having four major things. It means you're having a technique or a way of generalizing information given the abundant amount of information. You should generalize and get the general picture of information, unlike traditional approaches which only figure out the fixed patterns within a given problem and then only give fixed solutions which can't be adopted to different environments. Artificial intelligence technique here does the reverse. It gets generalization and understands by analyzing the patterns in the existing data how to use that information to give different to solve different case scenarios. Similarly, in the gate analysis project, this is what should be evident. You should be able to learn patterns from the available information, be it in a video and all whatever. I'm able to use that information to give more solutions in the proceeding patient gate conditions. Well, with that said, for an artificial intelligence, for a technique to be also said artificial intelligence, it should be able to be modified easily and then understood by the person who presented it. And then, just like I said, it should be able to be used in a different case scenario makes it scalable. That is simply what I can say about an artificial intelligence technique. To also say about having looked at what artificial intelligence technique is, we shall look at what problem solving is. Majorly, this follows some framework. If we are talking about artificial intelligence technique, it follows three major principles, where one is required to define his problem as precise as possible. Then analyze the structure of that problem. Generate the problem spaces, what we can call one as we look at, as we shall see in the successive slides. Once you analyze its structure, you should be able to represent it in ways understood by a computer. You should be able to represent it using different ways. We shall look at knowledge representation in the proceeding slides, and then choose the best technique for solving it. Choosing best technique, best is the key term here. How to choose it, how to conclude it's the best also takes different parameters. Does it save time? First of all, does it give the final solution? And all that. So in this particular context, our system defines gate problems as state transitions from normal, spanning from abnormal to normal movement pattern. So by analyzing the biomedical data present, or just extracting it from a given video of different working patterns. So this is it brings a range. So our system should be able to get that knowledge in a general way of it, and then represent it in a way it makes meaning of, and be able to reason about that data. So how can data be? How can knowledge be represented? You know, with what if not knowledge is to be represented simply, it can be follow a simple way. If we are using a logical way of representing it, we can use predicate logic, where we get a conclusion given some premises. For example, I may not like to give more examples to be for the fact of time, but it utilizes formal logic to express facts. Once these facts are expressed, they should be defined in a way that they form fundamental entities. Key aspects about that idea is extracted as entities, properties within it, and relationships. That makes the aspect of conceptualization key. After representing our information using predicate logic, we should conceptualize it and then interpret it. Interpreting is mapping those symbols and then the structures in that logical representation to that actual meaning in the real world scenario. For this case, it's gate analysis. So if you look at knowledge representation, it now defines the concepts like how one walks, how one runs. So using predicate logic, you can be able to represent complex health abnormalities and be able to follow all these steps, conceptualize and interpret. This makes our system possible to get meaning out of given information. With knowledge represented, we can look at some simple ways where a solution can be derived. That's knowledge representation. This is now problem solving. An example can be using these two different techniques, uninformed and informed. Just the word says informed versus uninformed. It means what matters is the knowledge base. Does our solution use the knowledge behind this to give a solution, or it just navigates the problem and then finds a solution? This gives an era of informed or uninformed. When we look at uninformed, basically we shall look at these two solutions or algorithms: the breadth first search and then the depth first search. The breadth first search explores all the nodes within the current depths, and then it only chooses that it looks to be better off. That's the breadth first search, and then navigates that, and then that will be the shortest solution. Unlike depth first search, which navigates, given it comes to a point where there are different ways of arriving at a solution, it navigates all before it backtracks. On the other hand, informed search, in contrast, uses information from previous knowledge and then be able to choose the best way of navigating the problem. Majorly this is used because you cannot navigate complex systems. It will take much time, and these are more efficient, we can say. Look at the grid-based search, the ESA search, and then the hill climbing. They really make computing so simple once one understands more about them. So with that said, in simple terms, you can look at problem solving as a state space search. You look at a problem in a way that you can represent it as states, where a transition from one state to another can be achieved using some operators. So in a when you look at problem solving as state space search, you look at the problem in form of problem states, where a transition from one to the other may lead you to the goal. So to start doing that, you should be able to have a starting point, and then a starting point should be able to your determinations to reach at the goal. So the starting point is the initial state, the goal state, and operators are the actions and rules that guide you as you transition from one state to another. And then this just simply connects to some spatial intelligence in navigating such trees. As you can see, as illustrated in our diagram one here, one may navigate from this green button to the red button, but in different ways. Well, in our gate analysis system application, we can see that states represent the different gate patterns. An initial state becomes an abnormal movement. So the goal states are health gate signatures, and operators are the corrective interventions that can be achieved. Our goal is to make people healthy. So we detect is first of all somebody abnormal. So how can we make him transition from abnormal to normal? Well, using the guiding instructions we call operators, we can transition somebody's life from abnormal to normal, transitioning that system. Well, so approaches in artificial intelligence, as said, are just basically one in different books can be said to be more than this, but to generalize, we can talk of symbolic approach, which looks approaches solutions in a way of just manipulating symbols, unlike the connectionist approach, which uses more information. For example, neural networks evident in the current era of artificial intelligence. Then the hybrid approach, which combines all the two. So our gate analysis system, when once it integrates the symbol manipulation approach and the neural network approach, can bring into classic models of artificial intelligence and make the model more super. And that's it. By using the hybrid approach, we shall achieve the best system ever. So how do the Gardner intelligence types apply in this artificial intelligence system? Well, just like I said long time ago, the linguistic approach, linguistic intelligence enables our system to analyze what to give to health personnel in form of natural language generation. Spatial intelligence would involve analyzing the different movements in a person as it moves in different environment to environment by tracking as one transitions from one point to another. Unlike the bodily kinesthetics, which specifically looks at the body's movements, spatial intelligence is more broader. Bodily intelligence is more specific. And then behind all this will be the mathematical aspect of it, which now brings the idea of learning and all the kind. Well, so that will now bring us into a point of reasoning and uncertainty, because as per this particular context, gate analysis cannot be achieved in a more simple way. We shall have more noise in our data, which I can also say call outliers. This data does not follow a regular pattern. So how can our model be able to analyze and give the best prescriptions even when data is disorganized, like having incomplete data or complex interactions, or having a case where a given factor is affected by thousands of other variables? How can it be able to adjust and generalize all that? Well, behind all this, there is probability theory, which enables it to treat a system in a way that, instead of giving a more specific answer that one is sick, but it just gives us the likelihood of one being sick. If one's like using the Bayesian algorithm, the Bayesian network, which gives the likelihood ranging from 0 to 1 in percentage form, can be converted to percentage in 0 to 100, ranging if 1 is 0% likely, then 1 is safe. We shall design boundaries where likeliness can be said to, we can generalize 1 to be safe and then be recommended to do some other prescription as a alternatives to avoid the threat. Well, that is what makes reasoning under uncertainty key in this aspect. We cannot finalize and give a final conclusion on one's possible state, but we can give a the percentage of likeliness that one can be as per a given scenario. Well, this can now bring us towards the end of our discussion, that's planning and decision making, where we can look at goal definition. Once a goal is defined, we shall look at how actions can be sequenced to arrive at a goal. Once those actions are observed well, we should be able to allocate resources accordingly and then see how to evaluate risks within that system. So all these aspects connect to majorly polykinetic intelligence through actions, sequencing, and frame problem in choosing the relevant preconditions. The data-driven planning uses frequent sequences from mining to guiding plans. Well, that as we've been saying all the time. So how can we integrate machine learning into this gate analysis system? Well, we can use supervised learning where we have our labeled data. Given these conditions, one is likely to do this. Or we allow our model to generalize, to picture the understanding of it given available data. And then it's able to get its own knowledge without explicitly being told what given data is all about. Or we can reinforce it. Once it learns what we expect, we give it a reward. Once it learns what we didn't expect, we punish it. So machine learning can completely be integrated using all the different approaches, and using all of them brings the best models. Choosing one may not be a better solution. So in this system, integrating all these concepts represent knowledge movement, reasoning under sensor uncertainty, and planning corrective interventions, and learning from patient outcomes to improve diagnostic accuracy. With all that said,